Hello, everybody. So last time, in the last video, we saw that we do have a problem, 3 SAT, and also SAT and circuit SAT if you want. All of those come from logic that is in NP and is NP hard, meaning that every other problem reduces to it and reduces to it in polynomial time. This in particular says that answering the question of P versus NP is the same as answering the question of whether 3SAT is a polynomial time algorithm. And that's true for any NP-complete problem. But the question that we're going to ask today is NP-completeness only about this kind of satisfiability problem, or there are more problems of this sort? And it wouldn't be surprising if we actually show that no, there are many problems that are NP-complete, and this means that all of those reduce to each other and everything else reduces to them, everything else in NP. So indeed, there are thousands of NP-complete problems, and they are in any area of computer science, and in fact, many other areas outside of computer science. For a while, NP-completeness was the major intellectual export of computer science in every area: biology, chemistry, physics, others. There have been various problems that turned out to be NP-complete. Since then, our understanding of NP-completeness has evolved, and actually this continued. So other fields have continued to adopt and show NP-completeness even after we learned to put NP-completeness in its right place. It's not the end of the discussion, but rather the beginning. And indeed, in some future video, we'll discuss a little bit what to do when something is NP-complete. But putting all of this aside, this is an amazing structure. There is thousands of problems. There is an entire book devoted to NP-completeness, and it's way out of date. So there's so many problems from so many areas, which are in some sense the same problem. All of them reduce to each other. Each one of them is the same as problem solving any of the rest and anything else in NP. So it's an amazing structure. And today we're going to start uncovering this structure. We won't get so far. You'll get a bit further in problem sets and quizzes. So given your favorite problem, pi in NP, how do you prove that it is NP hard? So to prove that it is NP complete, we need it to be in NP, but also, and that's the main thing, we need to show that it is NP hard. The way we will do it is to take some other problem that we know that it is NP hard. So far it's a 3SAT, for example. In the future we'll have more. And then to prove that sigma is polynomial time reducible to pi. This is where I want to reiterate how to interpret this notation. Sometimes it's confusing which problem reduces to which. What we have is that sigma reduces to pi, so kind of from left to right, and the smaller equal in some sense means that sigma is not harder than pi. It is weaker in a sense, weaker or equal. So this is how to interpret it, meaning that once we reduce sigma to pi, if we can solve pi, we can solve sigma. And if we cannot solve sigma, we cannot solve pi. So you take a problem that is already known to be NP hard, sigma. You show that it's polynomially reducible to the problem you care about. And this means that this is NP hard as well, because if sigma is NP hard and it reduces to pi, then pi is NP hard. Um, and the reason this is true is from the transitivity of this of polynomial time reductions, because for every a in NP, every a other a in NP, we know that a reduces in polynomial time to sigma because sigma is NP hard, and we just proved that sigma is polynomially reducible to pi, and we can conclude that a reduces to pi in polynomial time because of the transitivity of these polynomial time reductions that we discussed a couple of videos ago. Therefore, pi is NP hard, and if pi is also in NP, then it is NP complete. So we used polynomial time reductions to define NP completeness, and we are going to use it to deduce for many problems that they are NP complete, just like we did with undecidability and unrecognizability. We started by showing that ATM is undecidable, not ATM is unrecognizable, but we didn't continue to do diagonalization, but instead we showed reductions to ATM and then to problems that reduce to ATM and so on and so forth. So if we have NP, we have P, which is contained. We have sigma that we know is already NP hard or NP complete, and we show a reduction to pi, we can conclude that pi is NP complete. This is pictorially what we have because each one of these arrows give a reduction to pi. And so let's start with our first problem. The first problem will be, and several of our problems will be from the world of graphs. And a priori, it doesn't sound like a problem about satisfiability, but we will show how to cast it to satisfiability. So what's the clique problem? Given a graph G and a positive integer K, does G contain a complete subgraph of K nodes? The language, so this is the question, the problem, but the language, the related language is clique, which are pairs GK, such that G is an undirected graph with a K clique in it. And we actually already described that it is in NP, but it turns out that it is NP complete. This is one result of CARP. So we know that Cook and Levin showed their theorem. They showed that there is one problem that is NP complete. CARP had a paper that was incredibly influential following Cook's paper. And he showed these 21 problems from different areas and showed that all of them are NP complete as well. And that was quite, that gave a huge boost to this area because it showed that these NP complete problems are everywhere and this is a very rich structure. So clique is one of these problems that CARP showed to be NP complete. And the proof idea, we want to reduce it from an NP hard or an NP complete problem. And so far, you wouldn't be surprised that we only have 3 SAT. So we show that 3 SAT is polynomial time reducible to clique. So let me say something about these reductions, these polynomial time reductions that we're going to see. They are both easier and harder than the reductions we saw, the mapping reductions we saw in the chapter on computability. They're easier because they talk about different domains like graphs and number theory and logic, and they don't talk about computation. So I think one of the main things that made the mapping reductions confusing is that it was about Turing machines. So we wanted a transformation, which is a computation that takes one computation to another and argues about this computation. This was very confusing. On the other hand, there, if you got over the confusion, you could come up with a reduction almost mechanically. It wouldn't be very difficult. And here, every reduction will have some idea that is separate, some trick, and you'll need to think about it from scratch. So there will be a need for much more imagination, but perhaps it will be a little bit less confusing. In general, I find that many times, whatever is more trivial is more confusing because you have a proof and it immediately comes and it's so quick and you don't know, did I say everything? This is a proof, isn't it a proof? But one thing that we can still adopt from, if you remember, we had this kind of formula of how to do mapping reductions. One thing that we should do here as well is remember which problem reduces to which problem. So 3-sat reduces to click because 3-sat is already NP complete and we want to show that click is NP complete or that it is NP hard. And this would mean that it is harder than 3-sat. So this is just an intuition that it is harder, but this is the way I remember and I hope it will help you. Then you need to say, okay, if you take a problem from here, transform it to here, how does a problem here looks like and what does a problem here looks like? So an input for 3-sat is a formula, an input for click is a graph and an integer. So this means that we need to transform a 3CNF formula phi to a graph and an integer to GK. I won't repeat it again and again, but always start with the syntax. What kind of problem you need to reduce, which problem you need to reduce to which problem, how do inputs for this problem look, and how do inputs for the other problem look. And then what do you need to show? You need to show that the input for 3-sat is a yes instance, so phi is in 3-sat if and only if gk is in click. And here is another cautionary point that usually will create the reduction in a way that would make one direction easy, and we need to remember to prove the other direction. Because A, that's one of the things we need to do. We need not to forget it. But B, we need to, sometimes it will just be wrong. We'll build it in one way, but the vice versa would not be correct. So, okay, enough with the with meta discussions. Let's just dirty our hands and show that 3-sat reduces polynomial time reducible to click. We want to transform phi, and we want this transformation to be a polynomial. So, right, we need to show a polynomial time transformation and then to show the equivalence. So how can we encode a logic problem as a graph problem? It's highly non-obvious, but once we see the reduction, it won't be difficult. So a formula of a 3CNF formula has some M clauses, C1, C2, 3, C3 up to Cm. These are the clauses of the formula phi. And we're going to assign k, so this is the integer that we are creating, to be m, to exactly the number of clauses. We'll see why. So now we need also to define the graph G. The graph G will have, we need to define what are the vertices and what are the edges. So the vertices are going to be just 3m vertices, or more concretely, m groups of 3 nodes each, which is kind of convenient because each one of the clauses, it's a 3CNF, correspond to 3 literals. So group I of vertices corresponds to the clause Ci of the formula. And furthermore, we're going to label, this is just for the sake of the construction, we'll erase all these labels later, but at least in our mind, we're going to label each vertex with one of the literals of Ci. So now I defined what are the vertices, I need to define what are the edges. The edges are going to be between all pairs of vertices that are from different groups. We have M groups. We're not going to put any edges within a group. We're going to connect different groups. And we are connecting everything apart from those edges that correspond to a contradiction. So if we have one that is labeled xi and one that is labeled not xi, we're not going to connect it. In a sense, when there is an edge, it means that there is an assignment that satisfies both literals. And there is no assignment that satisfies both xi and not xi. Yeah, and as I said, you put no edges between nodes in the same group. And now when you're done putting all the edges, we can erase the labels. The labels just told us which edges to connect. So this is the entire reduction. We'll see examples and then we'll argue why it's if and only if. One thing that's already easy to see is that the reduction itself is polynomial time. You look at the formula, you count how many clauses. This tells you immediately what the size of the vertices set, and now you go over every two vertices and you can check if they should have an edge or not based on the corresponding literals in the formula phi. So it's not hard to come up with a polynomial time algorithm. Let's give an example, and this will also give us some intuition why the construction, which is not obvious. I don't know if it would be the first thing you would think of, but why this construction works. So if this is the formula, and note that it is a very, very non-interesting formula, but it's just an example that's easier for me to draw. So there are three clauses, meaning that there are going to be three groups of three vertices. And each one of these vertices correspond to some literal. So here you have x1 or x1 or x2, then therefore you have the literal x1, x1, x2. This is not x1, not x2, not x2. You have not x1, not x2, not x2. Again, I know that it is ridiculous. Why have these repeating literals, but that's a simpler example. Now we have the vertices, we need to create the edges. The edges are going to be, so for example, one edge that, so the number of vertices is 9, and this is one edge. So it goes from one group to the other. You never put edges within a group or within this group, but between these two groups you put edges. And note that the literals are consistent. x1 and not x2 can both be simultaneously satisfied by setting x1 to be true and x2 to be false. On the other hand, you don't have the edge x1 to not x1 because that is contradictory. And then you put all of the possible edges and you have this graph. And now you're asking, is there a clique of size 3? Because the number of clauses is 3. And here it's very easy to see that there are many cliques of size 3. And the question you should ask yourself, why 3 and what's the connection to the satisfiability of the 3 CNF? So for example, can there be a clique here of size larger than 3? Well, no, because a clique can only contain one of every group. Because there are no edges within a group, you cannot have two vertices from the same group in the clique because they don't have an edge between them. So this is just impossible. So the maximal clique is going to be of size 3. And in fact, if this is a satisfying assignment, then there will be a clique of size 3, because in each one of these clauses, there is going to be at least one satisfied literal. And if we choose the vertex that correspond to this satisfied literal, then all of those will have an edge between them because, for example, if we take x1 and if we take x1 to be, if we take x2 to be true, then this one is satisfied, this one is satisfied, and x1 to be false, which means that this one is satisfied. So this is not x1, x2, and x2. They can all simultaneously be satisfied. So this is one click. Good. So this kind of argue that if this has a satisfying assignment, this has a click of the right size. Turns out that also in the other direction. If you have a click, then you can have an assignment that satisfy all these literals of the click, and this would satisfy the entire assignment. Right. This is just an example with a larger formula, and now we will have 4 groups. We'll label them, and we'll put all the edges that are consistent. And still, this can be satisfied by setting x1 to be true and x2 to be true. It will satisfy all of that, and this gives us this click. So we saw so far a reduction. The reduction was polynomial time, and we need to prove the if and only if. That's what we need to show. So if phi, so let's do the if. If phi is in 3 sat, then gm is in click. And it will follow the intuition that we gave. The proof is that given a satisfying assignment, A of phi, for every clause in C, there is at least one literal of C that is set to true by this assignment. And for each clause C, let VC be the vertex from this group that correspond to a literal that is true by A. And I want to claim that this collection of vertices is a click. So the collection of VC from all these clauses in phi is an M click. And the idea is that if you have VC and VC prime, these are from 2 different clauses. Assume that there isn't an edge between them. What does it mean? It means that they are corresponding to some inconsistent literal. Let's say X and not X. But then the assignment A cannot satisfy both X and not X. And therefore, this is a contradiction. So therefore, VC and VC prime are an edge for every 2 vertices in S. So this says that this is a click and its size is M because we have a vertex for each clause and there are M clauses. So if phi is in 3 sat, we can conclude that GM is in click. Now we need to do the only if. So now if GM is in click, I want to show that phi is in 3 sat. And I want to say, okay, let S be a click of size M in G. And we're going to construct a satisfying assignment A of phi. So S contains exactly one node from each group. This is because of what we argued before. There are no edges within a group. And we want to say that there is an assignment that is going to satisfy all the literals that corresponds to vertices in S. So for each variable x in of phi, I'm going to create an assignment A that assigns x to 1, so assigns x to be true, if and only if there is a vertex v in S which is labeled x. So if one of the vertices in our m-click is labeled by x, I want to make sure that this is going to be satisfied, and therefore I'm going to assign x the value 1. If I don't have it, then I'm going to set it to be 0. In particular, if x is not in the click, but not x is in the click, then we will argue that x cannot be in the click, and therefore not x is not, then x is not set to 1, it's set to 0, and not x is true. So for all I, at least one vertex from the group I is in S, and therefore for all I, A satisfies at least one literal in the ith clause of phi, and therefore A is a satisfying assignment. And here again we use the fact that there are no x and not x labeled vertices in our click. Okay, so that was our first reduction. Let's do another one while we're on a roll. Independent set. Independent set, given a graph G and an integer K, is there a subset of vertices S of size K such that no two vertices of S have an edge? So if before with the click we ask that all pairs of vertices would have an edge, with independent set we want it to be the case that no pair of vertices have an edge. So we want to show that this is NP-hard. It is independent set is just the language of pairs GK, such as G is an undirected graph with an independent set of size K. And the click, as we remember, is one when there is a click of size K, so a group of where all edges within the set of vertices exist. So we want to show that click is a polynomial time reducible to independent set. This will show, so we already shown that click is NP-hard, and this will show that independent set is NP-hard. For both of them, by the way, we have shown that they are in NP already a couple of videos ago. So showing that they are NP-hard means that they're also NP-complete. I'll let you pause me and come up with this reduction. And now that you're back, let me tell you that the reduction from GK, it's going to be to G prime K. I'm going to keep K. And G prime is going to be 1 when I reverse all the edges and non-edges. So G prime is on the same vertex set V, but with the edge set, and it contains all the non-edges of G. So for every UV, if UV is not an edge in G, it is going to be an edge in G prime, and vice versa. If it was an edge in G, then it's not an edge of G prime. And this is now easy to argue that GK is in click if and only if G prime K is in independent set. It's exactly the same problem. We just switched edges and non-edges and switched clicks and independent set, and that balances out. So now we have 2 graph problems, and let's look at a third one. This one will be a little bit harder. So this is vertex cover. A vertex cover is a set of nodes that cover all the edges, which means that for every edge, at least one of its endpoints is going to be in this cover. So for example, for this graph, the star, what is a vertex cover. There are many vertex covers. For example, all the vertices are a vertex cover. So what is the smallest one you can find? Yeah, just the center of this star is a vertex cover because C is adjacent to all the edges. All the edges have C as one of its endpoints. How about this graph? So C is no longer a vertex cover because it doesn't cover the edge AD. What would be the minimal? Can we have a vertex cover of size 1 or 2? Well, the smallest one is 3. That's again not hard to come up with. So the problem vertex cover is a graph G and an integer K as we like. G is a graph with a vertex cover of size at most K. So with a clique and independent set, the challenge is to make them as large as possible. A vertex of size 1, a set of size 1 is always a clique and independent set because there are no edges. Vertex cover, you want to make it as small as possible because taking all the vertices is a vertex cover and you want to get the smallest one. Theorem is that it is NP complete. And again, what do you need to show? You first need to show that it is in NP. And what is the way to argue that it is in NP? Well, a witness of this vertex cover of size at most K is a vertex cover. So given a set of vertices, it is easy to first check that it is of size at most K, and then to check that all the edges are adjacent to one of the vertices. So it's not hard to show that it is an NP. It's exactly the way we've done it so far. And the second one is we want a polynomial time reduction from some problem. Here it will be independent set to vertex cover. And here we'll need to show that the reduction itself is polynomial time, and then it is the if and only if. So altogether there are 4 things to show: that it is NP complete, that you have a reduction, and the reduction is polynomial time, and then the if and only if. Try to think about a reduction. It's not as trivial, but it's interesting. So let's do that. So you want to transform G and K into G prime and K prime, such that GK is in independent set if and only if G prime K prime is in vertex cover. So that's the syntax. Both of them get a graph and an integer, so you want to transform a graph integer to another graph and another integer. So here is the claim that would help us. For every graph G and every subset S, I want to claim that the set S is an independent set if and only if its complement is a vertex cover. So S is an independent set if and only if V minus S is a vertex cover. Let's prove it. S is an independent set if and only if for every 2 vertices, it cannot be that both of them, so if both vertices are in S, then if both the vertex U and V are in S, then UV is not an edge. It's an independent set. There are no edges between 2 vertices in S. This is a complicated way to say something very simple. For every 2 vertices in S, there is no edge between them. So this is equivalent using a counter positive to the fact that for every 2 vertices UV, if UV is an edge, then either U is not in S or V is not in S. Because we said if both of them are in S, then UV cannot be an edge. So this is the counter positive of the first line. And this is exactly what it means for V minus S to be a vertex cover. Every edge has one of the vertices outside of S. In other words, every edge has one of the vertices in V minus S. Now, given that, the construction is going to be pretty easy. GK is an independent set if and only if G and the size of V minus K is in vertex cover. Because if you have an independent set of size K, take its complement, it's going to be a vertex cover of size V minus K, and vice versa. Take a vertex cover, you can turn it into an independent set. So this is the reduction. The reduction is polynomial time. You take the same graph G, you just count the number of vertices and let's say it's n and output n minus k. So our polynomial time reduction takes gk and transform it to g and the size of v minus k. Polynomial time reduction, and we proved the if and only if. Okay, so this is enough problems about graphs. Let's take a different problem from kind of a number theoretic problem, which is the subset sum problem. Again, it's not going to look like a logic problem, like a formula. It's not going to look like a graph, but it will have in it a graph problem. It will encode a graph problem in one way. So what's the problem? The problem is given a set of integers, of positive integers, a1 up to an, and another positive integer t, which is the target, we're going to ask, is there a subset of these integers in S, so a subset of the indices 1 to n, such that the target is exactly the sum of all these integers. So sum of I in A of AI. So you have a collection of integers, and you ask whether a subset of them sum up to this target integer t. And the subset sum is just the pair of these sets S and targets T, such that there is a subset sum. And so there is a subset A that sums up to T. So it's a simple number theoretic problem, very natural one, definitely one that we want to prove. And the theorem is that it is NP complete. So many things we want to prove are going to be NP complete. And I want, before showing you this reduction, how we show that it is NP complete, to tell you that there is an order n times t time algorithm for subset sum. So this algorithm is something that you can come up by yourself. It's not important for this class. It's a simple dynamic programming. So let me ask you, and you can pause on me to think, does this mean that P equals NP? We did find a good algorithm for subset sum. It's polynomial. And to a problem that it doesn't be complete, doesn't it say that P equals NP? So hopefully you stopped the video, you answered it, and let me reassure you that you came up with the right answer. So no, it doesn't say that P equals NP, because this algorithm is polynomial, but not polynomial in the right thing. You're supposed to be polynomial in your input length. So what's the input length? The input length is these n integers plus the integer t, the target. Definitely the length of the input is larger than n, because you have n numbers, you need to encode them. It will take at least 1 bit or more than 1 bit per integer, but it doesn't have to be as large as t, because to encode t, you just need log t bits. So you're looking for an algorithm that is polynomial in n and log t, not in n and t. I would just say that, in fact, if all the integers are small, imagine that all the integers are at most 50, then this is going to be a polynomial time algorithm, because t is not going to be too large. T is going to be linear in n. So in fact, if all numbers are polynomial in n, then the entire problem is going to be solvable. So this is what's known as pseudo polynomial algorithm, but it is not a polynomial time algorithm, and therefore it doesn't create any sensation. It doesn't show that P equals NP. Okay, you can ignore it if you want. And let's go to prove that subset sum is NP complete. By the way, why is so we're going to show it by a reduction from vertex cover, but we also need to show that subset sum is in NP. And again, this is easy. The witness for subset sum is just the subset of indices, and you can just sum up the numbers that correspond to these indices and see if they reach the target. Now we want to reduce a graph and an integer to a set of numbers. And let's talk about the reduction. Given gk, we're going to create a set of numbers and a target. So let's first, so G is a graph. It means that it has edges and it has vertices, and let's name them, or let's order them. So the edges are E0 up to EM minus 1. The vertices, without loss of generality, we can think about them as 1 to n. So all we did is just order the edges. So the instance is going to have n plus m numbers in addition to the target number. So let's see how to create these numbers. We're going to have n plus m, which is accidentally the number of edges plus the number of vertices, and this will mean that we are going to have a number for every edge and a number for every vertex. So let's start with the edge numbers. For every ej, we're going to have the number bj, which is 4 to the j in S. The node numbers are slightly more sophisticated. So the edge numbers are just 4 to the index of this edge. And the node numbers are 4 to the m plus sum of over all j's, such that the vertex I is one of the endpoints of the edge ej. So we're going over all ej's that this vertex touches of 4 to the j. So 4 to the m plus the sum of 4 to the j for every vertex that you touch. And the target number is going to be k times 4 to the m plus the sum of twice the edge numbers. So all the edge numbers twice. Let me go to the board to give a little bit more intuition about this construction. Let's give an example for this reduction. Let's take a very simple example. We have a triangle. It has the vertices 1, 2, 3. The ordering is not important at all. I'm doing it arbitrarily. And the edges E0, E1, E2. So what do we have here? We have 3 vertices, 3 edges. We're going to have 6 numbers. We're going to have the edge numbers. So this is 4 to the 0, 4 to the 1, and 4 to the 2, because we have just this E0, E1, and E2. And in addition, we have node numbers. Node numbers are going to be 4 to the m, meaning 4 to the 3, plus the edge numbers for the adjacent edges. So if we take, for example, E0, the adjacent edges are, if we take the first vertex, the adjacent edges are E1 and E0. So for the first vertex, the number that we're going to get is 4 to the 3 plus 4 to the 1 plus 4 to the 0. And the second one is 4 to the 3. Now we'll have E1 and E2. So plus 4 to the 2 plus 4 to the 1. And the last one is 4 to the 3. And it has the edges E2 and E0 plus 4 to the 2 plus 4 to the 0. So these are all the 6 numbers. And what's the target? The target is going to be k. I didn't specify k. So k times 4 to the 3 plus twice every vertex, every edge number. So plus twice 4 to the 2 plus twice 4 to the 1 plus twice 4 to the 0. And I want to, so this is the construction. These are the 6 numbers, and this is the target. So this is the target T, and these are A1, A2, up to A6. And the construction is done, but let's give ourselves some intuition. I mean, it looks very arbitrary and magical. Let's give ourselves some intuition of why it can work. And for that, I want to view all of this as numbers in base 4. It's not exactly right, but it's almost correct, and it's a very useful analogy. So let's think about the different places that we are going to have. We have 4 to the 3, 4 to the 2, 4 to the 1, and 4 to the 0. And let's see the vertex numbers. The vertex numbers, if we're thinking about it in this representation, is the first one is 4 to the 0, which is just 0, 0, 0, 1. And we have 0, 0, 1, 0. This is 4 to the 1. We have 0, 1, 0, 0. These are the 3 edge numbers. What about the vertex numbers? The vertex numbers are always 1 plus a 1 for each one of the edges that touch this vertex. And these are, we had these, so 1, 1, 1, 0, 1, 1, 0, 1, and 1, 0, 1, 1. And finally, we want all of this to sum up to k, and then 2, 2, 2. So this is the construction when thinking about it this way. And And this is kind of useful because we're going to sum up numbers, and I want to claim that we can. So this is why. Well, the first comment is, why isn't it exactly numbers mod 4? Just because k can be larger than 4, but all the numbers before are smaller than 4. And furthermore, we have the property that in every column we have at most 3 ones, right? We have one for the edge number and one for, so for every one of the first 3, we have at most 3 ones, one for the edge number and one for each one of the vertices that touches this edge. And therefore, when we sum these numbers, they will never exceed 4, and therefore will never affect the point above it. So if we sum up 4 to the I, it will never reach 4 to the I plus 1. So we can think about it as summation mod 4. And now we want to somehow say that if you have a clique, then you have a subset sum, and if you have a subset sum, then you have a clique. So let's start with a clique. So let's remind ourselves the graph looks like this. The only vertex cover has to be of size at least 2. So so the smallest vertex cover is of size 2. And let's take a vertex cover of size 2. Then I can take the 2 vertices. Each one of these 2 vertices is going to be a vertex cover, right? Each 2 cover all the edges. So let's just take these 2. These 2 together give me already the 2 here, and give me 1, 1, and 2. This is almost what we wanted. We wanted k, and k is 2 here, and 2, 2, 2. We can complement it by getting the vertex numbers, the edge numbers that correspond to places that we only have 1. So here it will be these 2. So starting from any vertex cover, we got a subset sum. What was the subset sum? I took all the vertex numbers corresponding to vertices in the vertex in the vertex cover. And then these vertices cover every edge either once or twice. So the numbers that I'm going to see down are either 1 or 2. Whenever they cover it once, I'm going to add the edge number. So that's one direction. This showed me that every vertex cover implies a subset sum. And now I want to say also that every subset sum will imply a vertex cover. And the reason for that is that I look at the numbers I collected. I will look at the vertices that they touch. These vertices are going to be a vertex cover. The reason, and they are going to be of size k, because the only way to reach this k is k is always the number of vertices you take. Because I only have here ones on this, I only have ones here. And therefore, to reach a k here, I need to take k vertices. These k vertices I'm claiming are going to be vertex cover because I need to reach 2, 2, 2 here. And these 2 can only be contributed by an edge numbers by 1. So if I reduce all the edge numbers that I touched, then just the sum over the vertex numbers is going to be at least 1 in each coordinate. Because if I have a 0 by the vertex numbers, the edge numbers cannot get me to 2. So we're going to go back to the slides and see it more formally, but I hope that I hope that this explanation on the board was at most useful, at least somewhat useful, and will help you understand the explanation in the slides. So we are back with the slides. This is again the construction. We had a graph. It corresponded to a set of edges and a set of vertices. We created the number for every edge, which was 4 to the j, where j is the index of this edge from 0 to m minus 1. And we had a number for every vertex, which was 4 to the m, plus sum of 4 to the j for every edge ej that the vertex touches. And we have the target number, which is k times 4 to the m, plus sum of the edge numbers twice. And so that's the construction again, and I want to prove the if and only if. If gk is in vertex cover, then st is in subset sum. So suppose C is a vertex cover. I'm going to take the numbers aj, and that corresponds to all, so these are the vertex numbers that corresponds to vertices in the vertex cover. And I'm going to add to them all the edge numbers that correspond to edges that are touched by the vertex covers once. So the vertex cover can touch these edges twice or once, but not zero, because otherwise it wouldn't be a vertex cover. And I'm going to take those that it touches once. As prime is the node numbers corresponding to nodes in C plus the edge numbers corresponding to edges covered only once by C. Claim the sum of all numbers in S prime equals T, and we saw it by an example. You can convince yourself. And yeah, and really the way to think about it is numbers base 4 and for vectors with m plus 1 components for 0, 1 up to m. And yeah, and we've done it on the board. Let's do the other direction. If st is in subset sum, I want to say that gk is in vertex cover. So suppose C and F are together the subset sum, meaning that the sum of vertex numbers corresponding to C plus the sum of edge numbers corresponding to F is exactly the target T, which is k times 4 to the m plus the sum of j equals 0 to m minus 1 of 2 times 4 to the j. This is target. Then I want to claim that C is a vertex cover. So the indices that correspond to the vertex numbers are a vertex cover, and it's of size k. So to do that, I'm going to subtract all the edge numbers from the above sum. And what's going to remain is just the vertex covers. And they are going to be, the sum that we get will still be k times 4 to the m, because the edges never touch this coordinate 4 to the m. The edges are from 4 to the 0 up to 4 to the m minus 1. So you don't subtract any of those. And then you have Cj, which can be 0, which can be 1 or 2 times 4 to the j. To begin with, you had 2 times 4 to the j for every edge. You removed some of the edges, so for some of them you're going to have 1. For the edges you didn't remove, you're going to have 2. So Cj is larger than 0. It's either 1 or 2. And what does it mean? It means that all the vertices touch. So you have k vertices, and they touch all of the edges, because the only way to get these numbers 4 to the j, if you have in a part of the vertices at least one vertex that touches this edge ej. Only for these vertices you have this number 4 to the j. So this means that it covers all the ej's. This implies that C is a vertex cover indeed. So, we had an interesting non-trivial reduction here. Let's mention a couple or a few more problems, and also show that it's not always so obvious. So, let's look at two problems, again graph problems, now about finding path. Let G be a graph, and S and T denote nodes. The shortest path is a tuple GSTK, where G has a simple path of length at most or smaller than K from S to T. And longest path is the same, but we want a simple path of length larger than K from S to T. A simple path is a path that visits every vertex at most once. So you don't visit the same vertex twice, you don't have a cycle. Now these two problems that seem similar, one of them is in polynomial time, one of them is NP hard, NP complete. Do you know which is which? Shortest path, you're going to see algorithms and CS161. It's the bread and butter of algorithms. All the search algorithms give you this shortest path. Longest path is actually NP complete. We're going to see, right. And in fact, we're going to see a reduction from another problem that I won't go show show its NP completeness. I think Sipser does, which is a Hamiltonian path. The problem, the Hamiltonian path is GST, and G is a directed graph with a Hamiltonian path from S to T. A Hamiltonian path is a path that visits all vertices. This is NP complete. The fact that it's NP, all of these problems is easy. Here you just give me a sequence of vertices. I check that it is a path in the graph that contains all the vertices, and it contains them once. And Hamiltonian path is NP complete. It is NP, and Sipser shows that 3-sat reduces to a Hamiltonian path in polynomial time. And we can show very easily that Hamiltonian path is polynomial time reducible to longest path. So GSTK is the longest path, and reduction is simple. GST is an Hamiltonian path if GSTV is in longest path. If there is a path that is of length, a simple path from S to T that its length is the size of the vertex set, then it is also an Hamiltonian path, because the only way to have a simple path that's length is the size of the vertex set is by touching all vertices. Therefore, longest path is NP hard. So as kind of in conclusion, we've seen quite a few problems. You'll see more in problems and quizzes. And this is just the tip of the iceberg. The other thing is that we've seen how powerful polynomial time reductions are. I hope this is one thing you'll take out of this class, the power of reductions. And one thing we'll talk about later is how to cope with NP completeness. So NP completeness, as I said, is not the end of the road, but just the beginning. So for example, even satisfiability, it's not the end. We just don't say satisfiability is NP complete, therefore we we ignore it. There are lots of SAT solvers. The SAT solvers don't work all the time, but they work on many interesting instances, perhaps in some domains on all instances we care about. But we can come up with problems with formulas that they cannot solve, but still in practice, satisfiability feels like a solved problem. To give another example, protein folding is an NP-complete problem, but our bodies fold proteins all the time, fortunately for us. And this tells us something interesting about protein folding. What are the kind of protein folding that happens in our body that is possible? What kind of instances our bodies have to deal with? So we'll talk a little bit about it. It's a huge area of research. NP completeness is not the end. We'll touch upon it very lightly. Thank you.